Listen to the talk of Riccardo Dondi about covering timeline in temporal graphs. So the floor is yours.
Thank you. So can you hear me, right? Even from Zoom? Okay, thank you. Okay, so this is the title of my talk, covering timeline in temporal graphs, complexity algorithms. And this talk is based on one joint work with Alexandru Popa from University of Bucharest and Manuel Lafond from University of Sherbrooke. So this is the outline of my talk. I will first give some definition. I will introduce the problem. Then I will, sorry, cannot see me. Then I will, present previous work on this problem and other related problems. Then the first result, so an approximation algorithm for the problem, the main problem I'm going to talk about, Minty cover. Another approximation algorithm for our restriction on this problem called one Minty cover. Then an FPT algorithm for the same problem with the parameter, the span of the cost of the solution, the span, it will be clear later. And then I will present some open problems. Okay, I will start with some definition. Probably all of you are familiar with temporal graphs, but just to be sure, okay, let's say a temporal graph is defined over a set of timestamps, a sequence of timestamps. Here I have 3 timestamps, so 1, 2, 3. The vertex set is not changing, while the ages may change. For example, at time 1, I see an edge between V1 and V4, and this is not present in time 2. You can see that V1, V4 is not defined, while, I don't know, I have V1 to V3, another vertex set. Okay, so this is the input we will have, so a temporal graph. And the problem has to define what is called an interval activity. So for each vertex, we have to define where this, where each vertex will be active. The reason is that this problem has been defined in social network summarization. So we want to understand when users are active. So we are to define the interval, a single interval where a vertex is active. And from a graph theoretic point of view, this means that when a vertex is active, it can cover ages, basically. That's what happens. So what is let's say the measure of an interval activity is basically the length minus 1 of an interval activity. So if I have a vertex which is active, for example, in exactly 1 timestamp, its span will be equal to 0. This is important, in particular for the FPT algorithm. And okay, this is just for a single vertex. And what we have to define is an activity timeline. So we have to define for each vertex an interval activity such that basically what I obtain is a set of basically a set of activity timelines that cover the ages of the temporal graph. So here is an example. So okay, it's the previous graph. So I have 3 timestamps. You can see that in gray, I have defined the activity for each vertex. So for example, vertex V1 is active at time 3, and it covers all the ages incident in V1. All V2 and V4, as V1, they are active in exactly 1 timestamp. So their span will be equal to 0 because it's the length minus 1, so it's equal to 0. Vertex V3 is active in 2 timestamp, t equal to 1 and t equal to 2, so in an interval of length 2. So its span will be equal to 1, okay, because it's 2 minus 1. Okay, so this is what basically we have to do, but the formal definition of the problem is like this. We have a temporal graph, and we have to define an activity timeline that of course covers all the ages of G, but of minimum span. So we have to minimize this function, which is called span. The other problem I will consider is a restriction. So again, we have a temporal graph. The only difference with the previous problem is that in each timestamp, we can see exactly 1 edge. Okay, so this is the only difference, and the objective function is, so the output is the same. Okay, so another way of representing graphs, temporal graphs we will use is with what we call union graph, which is a label graph. So you can see in the upper part, I have these 4 vertices and 3 timestamps. In the lower part, I have the union graph. So it's a label graph, and in basically the edges are labeled with the timestamps where this edge is observed. So for example, the edge between, I don't know, the pink should be, and the green vertices, you can see that these edges are defined at time 1 and 2. So in the union graph, I have a label 1, 2. This is the another way of representing that has been used in literature, and that sometimes we use in the algorithm. Okay, so previous work about this problem and related problems. So the problem was introduced by Rosenstein et al., and they showed that the problem is NP-hard in the general case. Then later, Froese et al., they showed that the problem is hard even when the graph is defined on 2 timestamps, just 2 timestamps. 1 timestamp, the problem is trivial because I can define everything active and the span is equal to 0. So, okay, every solution basically covers everything. I showed that the problem in a previous paper, I showed that the problem is NP-hard even if the graph is defined on 3 timestamps and I have some bounds on the degree of the graph, okay? And even this 1 min T cover, so where in each timestamp there is exactly 1 edge is NP-hard. Okay. On the other hand, Rosenstein et al., they show a positive result. Let's say if we want to decide, given a temporal graph, if it's possible to find an activity timeline of span equal to 0, this can be done in polynomial time. Is a reduction to sub basically. Okay, this is for the hardness result. Then we have some result about the parameterized complexity approximation, complexity or approximation algorithm and complexity. So parameterized complexity. So Froese et al., they showed that the problem is can be admits, let's say, an FPT algorithm for parameter the span of the solution, but just when the graph consists of 2 timestamps, is defined on 2 timestamps. And they also studied the parameterized complexity on different parameters, but in particular, even for other variants. So it's a more general. I think that we will hear later about this. For the approximation, actually, the 2 results of Froese et al. Can be applied also for approximation. And in particular, for, let's say, negative point of view, min T cover can be shown to be not approximable in constant factor, within constant factor, assuming the unique game conjecture. On the positive side, again, on 2 timestamp, it can be shown that the min T cover can be approximated within factor big O square root of log n. So this is about the approximation. Okay, so this is the main problem I will focus on this talk, but there are other variants of the problem that have been considered. The 2 main variants are defined basically changing the way the interval activity of vertices. I consider 1 interval, but can be more than 1 interval. This is something probably, again, we will on another talk we will talk about later. And also a different objective function. We want to basically minimize the span. So the span is the sum of the span of the vertices. But another objective function is minimize the maximum span a vertex has in a solution. And okay, this is this problem can be seen in some sense as a variant of vertex cover on temporal graphs. But I want to just know that there are other variants of vertex cover that have been studied recently in literature. They have been defined not exactly as this, so but I want to mention that they are works like that. Okay. Okay, I will talk about the first problem. So the first result, approximation algorithm for min T cover. So the approximation algorithm basically considers 2 cases. One case where basically we focus on the edges occurring at least 3 times in the temporal graph. And for this part, let's say we will give an approximation algorithm which is basically on vertex cover of this part of the graph. On the other, the other algorithm, let's say, consists of consider basically the edges occurring at most 2 times. And for this, we give an approximation algorithm using a randomized rounding of an ICALP formulation. And basically, we combine the 2 algorithms. Combining means that we take the best solution of the 2, depending on the, let's say, on the instance we have. So let's start with the first one. So the idea, okay, this is on the, let's say, upper part, we have the temporal graph, and then we have the union graph. And what we are going to do is we are going to pick only the edges that occur at least 3 times. So in this case are the one between the pink and the green one and the blue and the purple one. I don't know. So these 2 basically. And for these 2, what property help us is that basically for these 2, we know that at least one of the endpoints will be active at least in 2 timestamps. So we'll have a span at least of 1. So the approximation algorithm just basically pick a vertex cover. So we use, let's say, one of the approximation algorithm for vertex cover. And for each of these vertex, we make this vertex active in the whole time we have. So that's why we have this 2T approximation, because the 2 comes from the vertex cover, and the T comes from the fact that once a vertex is in the vertex cover, it will be active in the whole time domain, let's say. So that's why we have this 2T. Okay, so for when we have this, the other part, so the edges that occur at most 2 times, we define an ICALP formulation. Actually, it's for a slightly different variant of the problem, where we don't want, basically, we don't force, let's say, the vertex to be active in an interval, but can be active in several timestamps. And basically the cost of this problem is just the number of timestamps where a vertex is active minus 1. So for each vertex, and then we sum over all these vertices. This is basically the objective function you see where I write minimize. And okay, so for the constraints, okay, the first constraint just asks each vertex to be active at least once. Okay, this is not a problem. And the second one is the one related, let's say, to the fact that we want to cover edges. So when we see an edge between U and V at time t, we want at least one of the, let's say, variables to be equal to 1, or at least 1. Yeah, equal to 1 because it's in integer linear programming. Okay, so this is the integer linear programming, and we adopt let's say, a strategy similar to set cover. So we relax this linear programming, and we solve this relaxation, and then we use this approach. Basically, we pick the variables of the solution of the relaxation. We define another Boolean variable, capital X VT, and we define it equal to 1 with probability small x VT. This is the idea, and we can prove that basically with high probability we get a solution that covers all the edges, and that as a solution of a factor log n approximation, where n is the number of vertices. The problem is that this is not a solution to our problem, because in our solution we want the vertices to activity to be defined as an interval. So we apply the third point. So the idea is that we take one vertex. If it's defined in a single timestamp, we do nothing. If it's defined in let's say more than one timestamp, we pick the time, the minimum time and the maximum time where the vertex is active, and we made all these interval. We made the vertex active in all these intervals, and so that's why we get this big O T log n approximation. The log n comes from, let's say, the first 2 points, and the T comes from the third point. Okay, that's why we have this T log n. Okay. Okay, then I move to this one min T cover. So this is the restriction where basically in each timestamp only one edge is defined. So we applying the following strategy, because there are other, there are properties for this kind of instances that do not hold for the general temporal graph. So we consider a graph G having a span K, so admitting a solution of span K, and basically we focus on the vertices that have at least let's say more than degree 2. degree larger than 2. Okay, so for this, what we can prove? We can prove that this set has consists of at most 2k vertices. This is the first point. And the other property is that if we remove this this set of vertices from G, we obtain basically in the union graph and in the union representation of this graph, we obtain a set of disjoint paths. Okay, so actually, before applying this, we have to do some pre-processing, so solving this some easy part of the graph. But once we have solved this easy part, we get this, and when we have this joint part, this can be solved easily because it's they are not easy. We can solve it in polynomial time. I mean, it's not a problem. Okay, so basically what we can prove is this lemma that if we have an optimal solution for this restriction of Minty cover that has span K, there is a feedback vertex set of the union graph, which consists of at most 2k vertices. Okay, so this is the properties. And the algorithm then works like this. So basically we compute an approximation of the minimum feedback vertex set problem. So we compute a feedback vertex set F using, for example, the approximation algorithm of Boffner et al. If a vertex is in the feedback vertex set, then we make as before. Now we make this active in the all time domain, so between 1 and t. And we remove these vertices. What we get from the definition of F, we get that G minus F is a cyclic, and on a cyclic graph we can solve it in polynomial time. So that's the reason. And the overall stuff, let's say, is a 40 for let's say T04 T minus 1 approximation. So what the 4 come from the fact that basically we use a 2 approximation algorithm for feedback vector set. And sorry, I go later. And from this lemma here, we have a feedback that is at most 2k, where k is the span. Okay, and the t minus 1 or t okay comes from point 2, where since we make each vertex active in all time. Okay, so this is for the approximation. So now I present this FPT algorithm for Minty cover, where the parameter is the span of the solution. So for that, they show that this works when we have 2 time steps. So we were able to show that, let's say, general result on the general instance of Minty cover. So what is the idea of the algorithm? So basically, we use 2 main ingredients. One is iterative compression, the technique, well-known technique in parameterized complexity, and also an FPT reduction to this problem called directed pair cut. And I will try to explain you a bit about this. Okay, so high-level idea of the iterative compression. So what is the idea? Let's say that we order the vertices. So we have V1, V2, Vn. Okay, these are the vertices we have. And let's say that we consider only the vertices from 1 to h. And from 1 to h, we are able to compute a solution for the problem. I call it SH, that has span at most k. Okay, so this is something I have. What I want to compute is, starting from this solution SH, I want to compute whether there exists a solution where I add a new vertex. So the instance now is V1, VH plus 1. So I add a new vertex, VH plus 1. And okay, considering the solution SH, I want to compute whether there exists a solution SH plus 1 having span at most k for this part where I have a V1, VH, and VH plus 1. So this is the general idea of iterative compression. So some, let's say, ideas of the algorithm. So the idea is that since I have this solution SH, and I can branch on some, let's say, interval activities for some vertices. So the first thing, actually, what I'm doing is that, okay, remember I have a solution for vertices V1, V2, VH. What I'm doing is that I branch on the possible interval activity of the new vertex. So on vertex VH plus 1, I try each possibility. That's what I'm doing. Okay, this is some easy part, and there is some more complex part, let's say. So basically, for the vertex SH, I consider only the vertices having a positive span. The vertex having positive span, they will be at most K, okay? And but actually, I cannot branch on all of this. On a part of this, which I call NH, which I basically will be the vertices which are defined in the same time where the vertices have positive span in SH will be defined. I know this is a bit complicated, but for this I can branch. Okay, so what is left is basically the vertices that in SH have a span equal to 0, which can be many of them. I can have many of them. And the vertices for having positive span, which are defined in other position. And for them, basically, what happens is that I use this FPT reduction to the directed pair cut problem. So this is I try to show you in an example. I think I have time, yeah? Okay, so this is I hope that it makes it clear. Okay, so in the left part, I have the solution, let's say SH. So I have 3 vertices, V1, V2, V3. And here I just report 3 timestamp because I assume that on the 4th timestamp, no interesting ages is defined. I mean, no ages between V1, V2, V3 is defined. So you can see that I have this V2 and V3, they have a positive span. They have a span. They span actually 2 timestamps, so they have a span equal to 1. V1 has span equal to 0. Actually, I may have many of them. In this example, I just have 1, but I mean, in regular instances, I have many of them. Okay, so I cannot branch on this. So this is what I have. On the right part is what I'm computing. Actually, I'm trying to compute a solution for adding these new vertices, V4, which is in red because it's new. So you can see that I have 2 different colors on the right part. So this should be purple. I mean, my computer are the vertices for which I'm doing. I am branching, and the green vertices. So this. V1 and V3 should be green, okay? And this is the vertices for which I cannot branch. So what is the idea? For V4, as I told you, we branch. We say, okay, we will try all the possibility. And here, for example, I decided to consider the case where vertex V4 is active in 1. For V2, I can branch because basically you can see that in the left part, V2 and V3, they are defined in position 1 to 3, and V2 will be active between 1 and 3. So in position that are already covered by vertices having positive span. So I can branch. I have from T1 to T3. So for these 2 vertices, so the purple vertices, let's say, are the one related to the branching. V1, V3, I cannot branch. V1 because I may have many of them, and V3 because it's defined in another timestamp, a timestamp that was not considered before, let's say. So for this, I cannot show you how, but basically is the reduction that decide whether to define them to be active. Okay, so this is what happens. Okay. Okay, just to some, let's say, details about about this directed pair cut problem has been introduced recently and has been used to show some to give some fixed parameter tractable algorithm. So the problem is defined over a directed graph, and we have this directed graph G, a search vertex S, and a set of pairs P. And what I want to compute is whether there exists basically a cut of size at most K, such that after the removal of this cut, basically for each pair UV I have, at most one of the 2 vertices is reachable from S. Okay. So, the reduction is not so difficult, but it requires a lot of details, so I cannot show you all the details. The idea is that for all the vertices for which I didn't branch, basically, so the vertices in NH that are not in NH and the vertex VH plus 1, I construct a gadget for this. And this set of pairs P, which are defined in this problem, they are used to basically force the fact that that edges are covered, must be covered by the solution. Okay. Okay, I'm almost finished. Open problems. There are many actually open problems, but I point out two main, let's say, direction for the future. So one is for the approximation complexity. So actually, all the approximation algorithm we have, they have a factor which depends on t or t-1. So this is, and so it would be nice to get rid of this t, for example, or to prove that it's not possible to get rid of this t. So I don't know, is it possible to have a big O log n approximation algorithm for min t cover, or I don't know, a constant factor approximation for one min t cover? Also, this will be interesting. Okay. From the parameterized complexity, actually, the most interesting direction is probably to try to extend this algorithm we have for the definition of interval activity in exactly one interval to, let's say, more than one interval, even, I don't know, a constant, 2, 3, or I don't know, a parameterized by, let's say, the span and the number of them, something like that. So to extend it to other definition of the. And okay, that's all. Thank you very much. Thank you very much also for the invitation.
Thank you very much. Thank you very much. So questions?